Quantum computing feels like magic, but it's actually built on a solid bedrock of classical mathematics and machine learning. To master the quantum world, we first need to master the language of the classical world. Let's start with the basics. The single most important tool is linear algebra. In quantum, everything is a vector in a high-dimensional space. Quantum gates are essentially just matrices that transform these vectors, rotating them through Hilbert spaces. Understanding how these vectors interact through dot products and norms is crucial for predicting quantum states. Next up is probability and statistics. Quantum computing is inherently probabilistic, not deterministic. We deal with probability amplitudes, complex numbers whose squares tell us the likelihood of an outcome. This is where classical statistics meets quantum measurement, turning a cloud of possibilities into a single result. And that brings us to complex numbers. They aren't just imaginary here, they represent the phase of a qubit. Phase allows for interference, the secret sauce that lets quantum algorithms cancel out wrong answers. Now, where does machine learning fit in? Classical ML gives us the framework for optimization. Many quantum algorithms are variational, meaning they use classical optimizers to find the best quantum parameters. If you understand gradient descent in classical networks, you're halfway to understanding quantum machine learning. We define a cost function and use classical hardware to tune the quantum circuit until that cost is minimized. We also lean heavily on information theory. Concepts like entropy help us measure quantum correlation. Entanglement is the ultimate information resource, allowing qubits to share a state across vast distances. The beauty is that our classical intuitions often map directly onto these complex quantum structures. Mapping classical data into a quantum state, called state preparation, is a key challenge we face today. Quantum computers are naturally good at kernel methods, performing calculations in feature spaces too large for classical PCs. While the math is beautiful, the hardware is still noisy. This is why we use hybrid classical quantum models. In a hybrid model, the quantum chip does the heavy lifting, while the classical computer manages the overall logic. As we scale up, the linear algebra becomes more intense, involving massive tensor products. The foundations you build today in math and ML are the keys to unlocking the quantum future. Don't be intimidated by the hype. Stick to the fundamentals, and the quantum world will start to make sense. Linear algebra for states, probability for measurement, and ML for optimization. That's the quantum blueprint. Thanks for joining me on this journey into the foundations of the next computing revolution. See you in the next one.